Hello everyone, Assalamualaikum and good day. I'm Verawaty Ismail from Polytechnic Mukah. I'm here to present a paper on the effect of fiber direction on repairing tensile failure of glass fiber polyester composite. Before we go any further, let's take a look on composite material. Composite material consists of two or more natural or artificial materials combined to create a unique material having recognizable interface between them. The most consists of fiber as reinforcement and binded by adhesive called matrix. It is widely used in engineering, especially in buildings, structures, bridges, and transportations. Glass fiber polyester composite is, as its name implied, has glass fiber as the reinforcement and polyester as its binding material. Fiberglass composite offers high tensile strength, heat and fire resistance, and many other properties. But most importantly, it offers high strength to weight ratio for many applications. There are many ways of fabricating composites according to fiber direction or orientations, but there are three orientations that will be highlighted in this study. That is 0 degree, in which force applied in the same direction of the fibers, 90 degree, in which fiber direction is perpendicular to the applied force, and 45 degree, in which fiber direction is at 45 degree diagonal to the applied force. Many research had been performed to investigate the effect of fiber orientations in the mechanical properties of composite materials and proven to have major roles in increasing some properties of the material. Bakir and Hashim reported that the tensile strength is the highest in specimen with 0 degree fiber orientation and lowest in the specimen with 90 degree fiber direction. When analytical results indicate highest modulus of elasticity of the 0 degree fiber orientation and lowest at about 45 degree fiber direction. Because of the nature of the fiberglass composite, usually tensile failure can be repaired by mechanically cleaning and patching the affected area. However, there are limited studies on the effect of fiber direction after repairing tensile failure of the fiberglass composite. Hence, we carry out this study to investigate the effects of fiber direction on repairing tensile failure using glass fiber that as reinforcement and polyester resin as the binding materials. So materials that had been used in the experiment is the e-glass fiber fabric and unsaturated polyester resin is used as binding material. Predetermined fiber weight ratio is at 50-50. Preparation of all specimens are done manually using hand layup technique and cured at room temperature. Specimens were prepared according to STM D3039 standards, having 250 mm long, 15 mm wide, and 1 mm thickness. Tabs from the same material with 1.5 mm thickness were fixed to the specimens to prevent gripping damage, as shown in figure B in the slide. Next, the specimens undergo a preliminary tensile test to instigate tensile failure before repairing the specimens. However, the first attempt results in damage on the test specimen beyond repair, as shown in the first picture in the slide. So, we resort to make a notch at the middle of the test coupons to initiate tensile failure to make sure the tensile fracture at only one location and comes out with the damage only around the notch area. Then the fracture test coupons were repaired using the modified patented method for composite joining and repair at 0 degree, 90 degree, and 45 degree fiber direction, as in figure A, B, and C in the slide. Two tests were carried out for characterization of the repair glass fiber polyester composite. Tensile test is carried out to investigate tensile strength and modulus of elasticity of the materials. And burnout test is to derive the actual fiber volume ratio after repairing process is done on the original specimen. Results from the tensile strength is shown in the chart and tensile strength is highest on unidirectional specimen mended with 0-degree fiber direction with 119 megapascal, and lowest for 90-degree fiber orientation at about 32 megapascal. This is due to directions of repairing fiber is in the same direction as the previous fiber in the specimens, providing grips between the fibers. This suggested repairing tensile strength in the same direction of the former specimens as applied load is preferable to maintain as much tensile properties as possible in repairing fiber process. However, the tensile strength of the repaired composite had reduced by about 82% from the former 0-degree unidirectional specimen. This is due to uneven fiber alignment between the repaired and prior fiber, discontinuation of the fiber along the specimen, strength of the adhesive bonds, and effective repairing technique. The technique proposed by Zimmermann were unable to be fully adapted due to lack of thickness and width of the specimens, making the repairs only able to be performed on the top of the fracture line instead of both top and bottom side of the specimen. As of modulus of elasticity, it is derived from stress-strain slope from the tensile test. Test results in 45-degree fiber direction has the highest modulus at about 12,103 megapascal and lowest on the 90-degree fiber direction at about 7,240 megapascal. Based on the value of the modulus from the experiment, it can be inferred as the 45-degree fiber direction repaired specimens were the stiffest and only elongate slightly before break, while the 90-degree fiber direction showed the lowest stiffness. The modulus of elasticity on 0-degree is considerably high at about 10,000 megapascal with fractured pattern in figure A. It shows small elastic strain from the repaired part of the specimen and most of the repairing fiber pulled out from the specimen. However, this is contrasting to the study by Wang, 2014, which points out the Young's modulus of the 45-degree specimens is the lowest and the highest on the 0-degree fiber direction, analytically and experimentally. 45-degree fiber direction repairs may be able to exhibit higher Young's modulus due to the change in the fiber direction in the repair area. Change of direction provide graphs from prior specimen at 0-degree unidirectional and repair fiber and making it stiffer and unable to elongate well in the direction of applied tensile load, as in figure B. It is also fractured a part of initial specimen main body due to the graft from repairing fiber. From the burnout test, it is initially predetermined fiber weight usage actually is 50-50 ratio before repair. Results from the burnout test shows there was shortage in fiber weight due to loss of fibers during a braiding affected area and the addition of more resin during repair process. The fiber weight and volume ratio of 0-degree and 90-degree fiber direction shows more consistency at 0.47 and 0.34 respectively. However, the fiber weight and volume for the 45-degree fiber direction is the highest at 0.506 and 0.354 due to its fiber repair direction, which requires more fiber being added diagonally to repair fractured area. So the conclusion of the study, the experimental on strength for 3 different fiber direction on repairing tensile failure of fiberglass polyester composite has concluded that the 0-degree fiber direction provided the highest tensile strength and most ideal fiber direction for repairing tensile fracture of former 0-degree unidirectional specimens. 0-degree test specimens also have fairly high Young's modulus, which suggests this direction of repair fiber makes the repair specimen stiff and infer that there are still grafts between the prior and repairing fiber. Study is performed on actual fiber weight and volume ratio of average 0.483 and 0.347 respectively. That's all the findings from the study from me. Thank you very much for listening. Thank you all.